first tour, let's take a look at the field of nanoplasmonics. Now, whenever you throw the term nano in front of a word, half of people are going to be very excited about it, and the other half of people are going to pull an Elon Musk and roll their eyes. Well, nanoplasmonics as a field is about using teeny metallic particles, like little spheres of gold or copper, to dramatically enhance the interaction between light and matter. And these effects only happen if these particles are much smaller than the wavelength of the light. And since visible light has wavelengths in the hundreds of nanometers, that means that these particles need to have sizes of, say, 20 nanometers. In other words, the title of nano is well earned because it's an effect that doesn't exist if they were any larger. There is no field of, say, microplasmonics. But okay, nanoplasmonics is about using metallic nanoparticles to enhance the interaction of light and matter. That sounds a little vague, but these tiny metal spheres allow one to do some extremely incredible and very useful things. In fact, there are so many useful things you can do that I literally couldn't even fit it all in one video. So over the next 2 videos, we're going to be looking at the applications of these miraculous little metallic spheres. However, when discussing the behavior of these things, I'm only going to lay down, like from on high, their key properties. I'm not going to explain why they behave this way here. Instead, the 3rd video in this series will do that. So applications of nanoplasmonics is this video and the next. The physical origins of this behavior is then the video after that. I know, 3 videos, but take this as a sign that there is a lot of cool stuff we need to talk about. So okay, let's get started. In your basic nanoplasmonic scenario, you have light, like that from, say, a laser, which is shot onto these little metal particles. These particles might be suspended in a liquid, or they might be part of a rough surface, or they can even be placed on a surface in an orderly way. And when these nano-sized metallic particles are illuminated by this often monochromatic light, they have 3 important properties in how they are affected. Firstly, this light excites what are called plasmons in the nanoparticles. What are plasmons? Again, that's the upcoming 3rd video. But as a result, these plasmons dramatically enhance the electric field in a small neighborhood around the particle. So they're like little nano antennae or amplifiers that take the energy in the electric field of the light and redirect it to create their own field, but just in some small area around themselves. But that field is way stronger than the field of the incident light. This is called electromagnetic enhancement. So it's like the impinging light starts the party, but once the plasmons in the metal get involved, it gets dialed up to insane rager. But by how much is this field enhanced? Often by a factor of thousands, or even hundreds of thousands. It's an enormous boost. So that's our first key property. They boost the strength of the electric field in their neighborhood. The second property is that this plasmonic response of these nanoparticles doesn't treat all wavelengths or colors of light the same way. In fact, if you plotted the strength of electromagnetic enhancement versus wavelength, you'd find there's something called a plasmonic resonance at a specific wavelength. So in a sense, these particles are like little singing, like wine glasses, where there's one specific frequency that is a natural resonance for them and makes them sing, so to speak. Though, remember, we're talking about light here and not sound. Now, the frequency of light at which this resonance occurs isn't some universal property. It's not some fundamental property of the cosmos, but rather it depends on things like the material property of the metal, the shape and size of the nanoparticle, and importantly, and this is our 3rd important plasmonic property, it depends on the environment around the nanoparticle. If I have a metallic nanoparticle in a vacuum, and it has a certain plasmonic resonance, and then I go and place it in, let's say, water, the frequency of this resonance will redshift. It'll move to a lower frequency. Another way of saying this is that if I illuminate this particle with white light, which contains all colors, its color will shift depending on its shape and its surroundings. So the key properties are that when a metallic nanoparticle is illuminated, 1, it creates a region of dramatically enhanced electric field directly around it. 2, it has a resonance to this electrical response, a signature frequency depending on its material and shape. And 3, this resonant frequency shifts in response to changes in the medium around it, the medium it's immersed in. So let's talk about applications. But remember, in this video, we're only doing about half of the applications. In the next video, we're going to talk about sensing and scanning applications that mostly are based on this 3rd property. Here, we're going to talk about what you can mostly do with these 2. One way you can exploit these properties is to basically recognize that they allow you to create hotspots of an electric field, concentrating it into a very small area around that nanoparticle. This concentration of the electric field can then also drive absorption of the light, which then leads to basically a localized heating effect. One particularly dramatic application of this is using metallic nanoparticles. You can literally boil water using concentrated light at temperatures far below boiling. When the nanoparticles enhance the field of the laser light, it creates a bubble where absorption of light is dramatically higher and thus heating is similarly enhanced. You therefore get little bubbles of vapor that are nucleated by these particles and float out of the water as steam. Of course, you don't have to only do this with water. This allows one to, for example, catalyze a chemical reaction using light at illumination levels where it naturally wouldn't occur. But going back to this heating of water idea, this also has applications to create so-called hybrid photovoltaic thermal cells, or HPVT. Solar cells for power generation don't actually use all the wavelengths of light that the sun emits. In fact, they don't use any light at all above a certain cutoff wavelength, which is related to what's called the band gap energy. Well, houses need power, sure, but they also need hot water. And if the solar cell isn't using these wavelengths anyway, why not a layer on the top of the cell with nanoparticles suspended in a transparent fluid? The idea being that the nanoparticles are engineered to have their plasmonic resonance in the range of unused wavelengths, and thus drive absorption heating of the fluid. The wavelengths that the cell does use pass through unaffected. There's also yet another way you can use this